Thank you very much for the introduction, and many thanks for giving me the opportunity of being here today. It's a great pleasure of being in Scotland. I'm quite emotional with Scotland. I lived here for a couple of years. I spent 2 amazing years in Scotland, so I'm really always happy to be back. So thank you, and many thanks for organizing this very nice workshop with many different topics. I'm enjoying very much. So what I want to discuss today is, giving a bit of an overview of what these reachability categories are, and especially give a bit of motivation and describe their use in, let's say, commuting algebras and applied topology. So good. So let me say a few words about the motivations behind this work. So our first motivation was basically let me say topological data analysis. But these reachability categories have many different, let's say, applications. I'm going to discuss a tiny bit about ring theory, but one of the application, or at least connection, is there with magnitude homology, and I needed to say it because I'm in Scotland and the magnitude homology or magnitude was born here, and you have many of, I'm pretty sure that most of you know about magnitude homology or magnitude. So I'm not going to delve into details in that direction, but also because of time reasons. I'm also sure that Scotland has a good advantage in that regard. The other topics or the other motivation was from topological data analysis, I was saying. And in particular, if you started with some data, what you can do is to associate to it filtration of graphs. And we are interested basically in understanding whether homological, categorical, and topological means can give us invariance of these graphs. And in particular to expand or, have new information about graphs and about data. And there are many different approaches. The first one, for example, is related to magnitude homology, and this is path homology. But as we were saying at the previous talk, we were discussing about homology of 3 categories with coefficients in a monoid. This is also part of the picture, or we could use also posetal homologies, or for us, the motivation was actually to use Hochschild homology in this picture. And when I give this talk, I always like giving this non-commutative diagram, because basically, if you want to understand data or filtrations of digraphs, at some point you really need to represent the category of directed graphs in a category in which you can do some homology or homotopy. And for example, as I was saying before, you can represent the category of graphs in the category of categories itself. So this is the 3 functor we were describing before. And we can also describe graphs in terms of posets, simplicial complexes, or in terms of algebras as well. So there are many different aspects that we can use, and today we will touch some of them. So let me say a bit of the framework. So I'm going to repeat, so I'm really happy that John gave the talk before me, because now I can speed up on this part. Basically, the only term that's different from before is the term quiver, and everything is alike. So for us, a quiver is just a functor on a category with 2 objects and 2 morphisms, source and targets. And the functor leads to finite sets. So all quivers are going to be finite for us. This is something that I want to make sure about. And what we're going to need also is the notion of paths or directed paths, or before it was called edge paths. And but also we're going to use simple paths, which are these directed paths where the vertices are not repeated. The first observation is that morphism quivers and simple paths or directed paths to directed paths. And in fact, we can build up, as described before, the 3 category on a quiver. So, so the objects are the vertices of the quiver, and the morphisms are going to be the paths from the objects. Another remark I want to give you here is that if Q has directed cycles, then the category you generate this way, that we denote by path Q, is infinite. It's not finite category. And this is because you have many loops. So this is the first representation of graphs. So for each graph, we can associate a category, as I was saying, but there are other representations of the category of graphs in, for example, algebras. And the free way or the easy way to associate to a graph an algebra is through categories, is the one to apply the to construct the category algebra of a category, which I remind you is the free category generated by the edges, by the morphisms in the category. And the product is given by the composition of paths. So now category algebra is always going to be associative, and they're unital if and only if the category is finitely many objects. This is going to be important later as well. Yes. I want to give you a couple of examples that are going to be important later on. The first example is what happens if you start with a free category generated by a graph, or the category algebra is better known as the path algebra of the quiver. Whereas if you started with a poset, let's say finite poset, then the category algebra associated to the poset seen as a category is better known as incidence algebra of the poset. And now we already have two different ways to associate, for example, to a poset or to the graph underlying the poset, two different algebras, which is the path algebra and the incidence algebra. And this is a result by Ortega about 20 years ago that says that if the poset is finite, then the path algebra and the incidence algebra are going to be isomorphic, if and only if the poset was a tree, which means that all our ideals are well ordered. We want to categorify or at least explain this result categorical means. And from one side, we have the free category generated by the graph. On the other side, the category we are interested in is the reachability category of the graph. The term reachability comes from graph theory. You might be knowing this as posetal reflection of categories, and we're going to go back to it later. But the formal definition is that the reachability category of a quiver is the category with the same objects as the path category. So these are the vertices in a quiver. And for two objects, V and W, there is one single morphism, if and only if there was a path from V to W, let's say. And otherwise, we put the empty set, a set of morphisms. So basically, we are squeezing in all possible paths with same source and target. And that's also the reason why of calling it reachability category. And as an observation, everything is functorial here, so we can go from quivers to thin categories. And this is thin because, of course, it has only one single morphism. And the first remark in the same direction of Ortega's observation is that if Q is a polytree, which means that the underlying undirected graph is a tree, then the path category and the reachability category associated with the quiver are isomorphic. And this is easy to see because if you think about it, both the reachability category and the path category have at most one morphism for each pair of objects. And this gives you the isomorphism there. However, we want to describe it, in better terms, or let's say in more generality. And to do this, we need the notion of quasi-bigons. Let's say that for us, a quasi-bigon is the quiver like in the picture. So we have two main objects, let's say X and Y, and we have two different ways, two different paths from X to Y, let's say via the VIs or via the WJs. And we are interested in this sort of sub-quivers in our given quiver. And the reason for this is because if you started with a connected and finite quiver, then the path category and the reachability category are isomorphic if and only if the quiver is started with has no directed cycles, no quasi-bigons. So we have, let's say, a generalization of Ortega's result, but in categorical terms. So let me show this example, very easy example. So this is not a polytree because the underlying graph is a cycle. On the other hand, the path category and the reachability category are still isomorphic. Let me give another example to have a bit clearer what's happening there. So if you started instead with the square quiver where we have 4 objects in 2 different ways from 0 to 3, let's say 0, 1, 3, and 0, 2, 3, then the path category associated to this quiver has 2 different ways to go from 0 to 3, and these 2 morphisms are not alike, are not the same. Whereas in the reachability category, where we are collapsing all possible paths with same source and target, these 2 ways become just 1 morphism. And this is the main difference between the 2 categories. And in fact, they are not isomorphic and not even equivalent. Which leads me to the question, okay, whether, so we classified when the path categories and the reachability categories are isomorphic, but nobody works with isomorphic categories. So what we want to do, at least, like in topological terms, to describe when reachability categories and path categories are equivalent or homotopy equivalent. And to do this, I'm going to use the nerve functor. So I just remind you that if the category is as an initial object or a terminal object, then the geometric realization of the nerve of the category itself is going to be contractible. And equivalence of categories is sent by the nerve functor to homotopy equivalences. And a result that it's going to be needed here is a result by Citteri of about 25 years ago, saying that if you start with a quiver and you take the free category generated by it, and you apply now the nerve functor and you take the geometric realization, well, this is going to be just a bunch of S1s, of spheres of dimension 1, which gives us really like the intuition of what we were discussing before as well, that quivers are basically one-dimensional objects. And also not just from the categorical point of view, but also from the homotopical point of view, we cannot expect to have higher dimensional invariance because, well, if if quivers have this way, the homotopy types of a one-dimensional object, we have no chance to get higher homotopy groups. And to go back to the same quiver, the square quiver of before, for example, the path category, the free category associated to the quiver has the homotopy type of S1, whereas the reachability category associated to it is contractible. So it has the homotopy type of just 1 point. So they can't be equivalent because we said that the nerve preserves the equivalences. So this is not good, but at least it gives us a way to deal with the question of when the path categories and the reachability categories are equivalent. So let me remind you that a quiver is called strongly connected if for each for each pair of objects, let's say X and Y in the quiver, you have a directed path from X to Y. Yes? And if Q is a strongly connected quiver, then the result is that the reachability category is always contractible. And as every presentation has to have at least 1 proof, at least for me, this is the proof, the almost complete proof for today. And what's the idea behind the proof? Well, you have the reachability category from one side. We consider the category with 1 single object and the identity on the other side. Now you've defined a functor from the 1 category to the reachability category by choosing where to send basically the 1 object in the category 1. And let's say it's sent to the object, any object Q in Q. And this describes basically a functor from 1 to the reachability category, which is an equivalence of categories. And as a consequence, the nerve of the reachability category is homotopic to the nerve of the category with 1 single object. And this last is contractible, which implies the contractibility of the reachability category. So let me go back now to at least a sort of classification of the equivalences between the path categories and the reachability categories. So the fact that strongly connected quivers are contractible allows me to use the condensation of quivers to prove that if Q has no quasi-bigons, then there is an homotopy equivalence between the nerve associated to the free category on the condensation of Q and the nerve on the reachability of the quiver itself. So basically the reason of this is that if the strongly connected components do not matter up to homotopy, then I can collapse all of them. but collapsing all of them, the homotopy type is preserved, and this is precisely what the proposition says. So we have up to homotopy equivalence, at least the reachability in the category and the path category are quite alike. Unfortunately, I put the assumption that we have no quasi-bigons. What happens with quasi-bigons? Well, it happens that we have basically any homotopy type. So if the path category is intrinsically one-dimensional, the reachability categories can be of any possible dimension. And the way you can see it is that first observing that if you start with a poset, then the reachability category associated to the poset is the poset itself. But then you can take as a poset the phase poset of a simplicial complex. The nerve associated to this phase poset is going to be the barycentric subdivision of the complex itself, which means that the reachability category can have, the nerve of the reachability category is homotopy equivalent to X. And this implies that it can have homotopy groups of any dimension of any sort. So the two categories of the reachability and the path category cannot be alike when there are quasi-bigons. But this might be disappointing, but it actually is a good news, at least for our motivation. There was the motivation to apply basically these categories in applied topology or topological data analysis. I want to describe a bit how we use this, for example, in ring theory. But before doing that, I need to remind you that basically you can consider skeletal categories as in the category of categories. And this is a result by Bourseau, Campanini, Gran, and Toyan of a couple of years ago, that the category of skeletal categories is reflective in the category of categories, which means that I can pick any category and choose in a coherent way its skeleton. So this means that I can cook up a functor which goes from thin categories to posets. And this is usually called the posetal reflection. This is why I've said at the very beginning that you might know the reachability categories as just posetal reflections of normal categories. But this way we obtain a way to go from quivers to posets I could have done directly, but this way we know that we can associate to quivers both reachability categories and posets, and the two are actually equivalent one another. And this is an important step. So the reachability category and the reachability poset are equivalent because the reachability poset is the skeleton of the reachability category. In ring theory, if you start with a quiver, you can consider what's called the commuting algebra of the quiver. This is known as to be the path algebra generated by the quiver, where you mod out the parallel ideal. So this is the two-sided ideal in the path algebra, which is generated by paths with same source and the same target. But on the ring level or categorical level, this is precisely what we were doing from the path category to cook up the reachability category. And in fact, if you compute the category algebra of the reachability category, then this is isomorphic to the commuting algebra that I just defined. Another piece of information that I need to give you or to remind you is that if you start with two rings or two algebras, they're called Morita equivalent if the categories of representations are equivalent, either left or right modules. And it is known that if C and D are equivalent categories, but with finitely many objects, then the category algebras are Morita equivalent. From the point of view of ring theory, this is quite important because they have equivalent categories of modules. And the result that we were able to reprove is the following result by Green and Schroll of last year that says that the commuting algebra of a finite quiver is Morita equivalent to the incidence algebra. And I think I could give this as an exercise now because it really follows from the definitions, from the categorical definitions we gave. And the reason is that, well, if you started with a quiver, we could associate with the reachability category and the reachability poset, and these two guys were equivalent. But as Q was chosen to be finite, then the category algebras are also Morita equivalent. If Q is finite, then the categories associated, the path category and the reachability category have finitely many objects. And by using the result of the force, we can show that these are Morita equivalent. But from one side, we have the category algebra of the reachability category. This was the commuting algebra. On the other side, we have the category algebra of the reachability poset, which is a poset. So the category algebra associated to it is an incidence algebra. So and this gives back the results, the theorem by Green and Schroll. Furthermore, we can show that if the commuting algebras of Q and Q prime are equivalent, then the reachability posets are actually isomorphic, and this is an if and only if. So by using these categorical terms, we are able to really transfer what happens on the level, on the algebraic level, to what happens on the, let's say, combinatorial level. We see many, many times, let's say, in category theory. And here, so if I wanted to give, like to squeeze down in just one single diagram, what I described so far is this diagram, let's say. So I can go from quivers to poset by taking the reachability poset. And then I can construct the incidence algebra, or I could have gone directly from quivers to algebras by using the commuting algebras. And this diagram, it happens to be commutative up to Morita equivalence. It's a theorem by Delambroge and Taboada that says that equivalent structure, the category of linear categories, as a weak equivalence is the Morita equivalences that we described just a couple of minutes ago, and the cofibrations are functors which are injective on objects. And what we're working on now, what I would like to know is whether there exists an homotopical enhancement of, let's say, this diagram above. Instead of being commutative up to Morita equivalence, I would like to put in a category of quivers model structure for which the category is now commutative on the nose. But this is yet an open question. But if you have any ideas, please let me know. There's another result of, let's say, maybe it was in the late 70s by Stanley that says that going from posets to algebras by taking the incidence algebras is conservative. And this allows us to say that if the commuting algebras of two posets are isomorphic as K algebras, then also the reachability categories were isomorphic. So we can pull back also morphisms between commuting algebras to morphisms of reachability categories. And I was also mentioning the fact that path categories are basically one-dimensional, whereas the reachability categories are of higher dimension, of any dimension theory. And but what we can do is also to bound this dimension. So we could use the global dimension in ring theory as the soup over the sets of projective dimensions of modules. And the result is that the corollary is that the global dimension of the commuting algebra is bounded by the diameter of the quiver. So we really have on combinatorial terms a bound also on the dimension, also on homotopy groups or the likes this way. So let me go back to our motivation. So this was the application in ring theory, but our motivation was stemming from topological data analysis. And in particular, we wanted to use Hochschild homology, which is an homology theory for algebras in the context of topological data analysis. The reason for this is that, let's say, Hochschild homology and simplicial homology are quite related, but they're different. And a result of Appel says that if you start with a quiver and you take the path algebra of it, then a path algebra is one-dimensional, and also Hochschild homology is going to be at most one-dimensional. So if you want to cook up nice invariants of data, or this is not the way. Let's say you're gonna look at only connected components and all possible paths in the quiver, which is not satisfying. So the reachability category was a way to sidestep this issue. And how do we do that? Well, let me remind you that the reachability categories and the reachability posets are equivalent. So I can use the category algebras associated to them. They're still equivalent. They're Morita equivalent. And thank you, I'm almost done. And and the so the Hochschild homology is an invariant up to Morita equivalence. So this means that the Betti curves associated to the path to the category algebra associated to the reachability category and the reachability poset are the same. So from a topological point of view, the Betti curves are really the same, and we can either use the reachability categories or the reachability posets. So we can, once we have some data, we can associate to them a filtration of graphs as in topological data analysis and associate to them the reachability posets. Consider the category algebras, the incidence algebras associated to them, and apply Hochschild homology. This is, we might call them in analogy with the persistent Betti numbers, the persistent Hochschild homology curves. So this way we have some invariance that can be given to a machine learning algorithm. And the main observation is that its persistent Hochschild homology curves are actually simplicial themselves. They agree with the simplicial Betti numbers of the nerves of the reachability categories. So from one side is related to what happens in usual classical persistent homology, but from the other side, if you started with, it's quite different. And this is ongoing work with Henry and with Nicolas Meadows, that we were showing what's the difference between really applying Hochschild homology or simplicial homology on some concrete data, real data. And the last bit I wanted to say, because we showed us some relation with ring theory, with topological data analysis, I want to show you some connection also to magnitude homology, or basically to combinatorics. And this is in terms of complexes of injective words. So this is, if you start with any set, you can cook up this simplicial complex, which is given by all possible ordered sequence of words with distinct lectors in W, in the set you chose. And this simplicial complex was shown by Farmer to be basically a wedge of spheres. The number of spheres is related to, let's say, representations of the symmetric group, but I'm not gonna use this fact. On the other hand, so we have seen that associating to graphs some invariance is always interesting. So what we could do is to extend the definition of complex of injective words from, let's say, sets to graphs. And there is a standard way. The words basically are going to be on the letters, which are the vertices of the graph. And we put two letters one after the other if there was a direct edge in the quiver. So once we define the complex of injective words on a graph this way, what we showed with Giulia Maria Menara is that this is complex, is homotopic to the injective nerve of the reachability category. So the injective nerve is a variation of the usual nerve of categories, but in fact on posets the two are the same. And on the other hand, so this is also related to the directed flat complex if you're aware of it. But on the other, but regardless, if Q is a poset, this is the usual nerve. So if Q happens to be a poset, our quiver was the underlying graph of a poset, then the complex and injective words in the quiver are, give the nerve of the reachability category, and this means that this is not simply a wedge of spheres, because we've shown that the reachability category can have any sort of homotopy. And this is the last bit I wanted to say, and I conclude here with some open questions that are here, but I'm happy to answer some questions if that. Thank you.